Hello everybody, my name is Torsten Hoefler. I'm a professor at ETH Zurich, and today I want to present the random access Salishan talk that I gave earlier this year at the Salishan Lodge. So it was all about Fortran. So the title is "Fortran is Dead, Long Live Fortran." Actually, many people at the Salishan meeting somewhat declared Fortran as a language that is very much of the past and deserves to be retired. And of course, what you do first in 2023, or now probably 2024, or even later, is you ask your favorite language model, in this case Bing Chat, for an opinion on some nice poem for Fortran's retirement party. So you can read it yourself, and it's actually a quite nice poem. But then you may go one step further, because many people said, well, Fortran is not just retiring, it's actually already dead. So if you now ask your favorite language model in, again, Bing Chat, please write a poem for Fortran's funeral, even the artificial intelligence, the language model itself, disagrees that Fortran should be buried. So I'm sorry, but I don't think it's appropriate to write a poem for Fortran's funeral. Fortran is still being used today and has contributed to many scientific discoveries and technological advancements. It is not dead yet. However, if you have any other requests, I'd be happy to help. So it's not dead yet. And this is actually part of the talk that I wanted to give here and really change the opinion of the audience, where many told me over breaks that this is Fortran is basically over and needs to be replaced. So I want to throw a little bit of a different view to the audience. Even though we can talk about the ecosystem later, that Fortran is struggling in many, many ways. But let me give my pitch. This is a talk that has been put together basically in a couple of hours online, pretty much while listening to other talks at the Salishan meeting, the 42nd year Salishan meeting. So what was discussed at this meeting is really all about DSLs, domain-specific languages. And we have many, many DSLs, especially in the environment of the DOE, Raja, Cocos, the Swiss grid tools, PyTorch, TensorFlow, mainly driven by companies in the machine learning area, and many, many more. So if you look at those DSLs, they're basically a way to up-level performance libraries. So they're more flexible than just simple BLAS, LINPACK, or LAPACK calls, and they give you about the same performance. That's at least the promise of these DSLs. Well, if you actually look at many scientific problems, at the core of those is really the manipulation of arrays with scientific formulas. And if you think about it, Fortran, a formula translator, is somehow the oldest domain-specific language for the domain of scientific calculations, which manipulates arrays with scientific formulas. So it's literally the formula translator. It was invented by a Turing awardee, John Bacchus at IBM. At the time, when you actually go back and read the good old Fortran discussions, people were skeptical that it would beat assembly. So people were, in 1957, writing in assembly, and they thought it would never be possible to have a high-level language at the same performance as assembly, so we should all stick to assembly. And literally, Fortran gave rise to the first optimizing compiler. So it is a very, very important historic language that really laid the groundwork for many things to follow, many important climate simulations and weather simulations. But even in 2021, if you look here, Fortran returns to the top 10 programming languages. And of course, while it's still widely outperformed by C and also Python in this language, but this is an interesting one. So Fortran has seen some kind of comeback, and just looking at yesterday's TIOPE index, Fortran is still in the top 20. So we are talking 2023 now, and Fortran is on a rise, so with a positive gradient in that list. So that's actually quite an interesting observation, I think. So it's definitely not losing popularity. But of course, many people argue that NumPy, the Python version, is the new Fortran. And if you look at the list in March 2023, Python has taken the top spot from C, which still used to be the top language in 2021. This is partially due to the ecosystem, or I would actually say largely due to the ecosystem. It's not because Python is the most beautiful language for implementing formulas. In fact, Fortran is not a bad language for implementing formulas, but Python in the PyPy package index has more than 400,000 projects. So the ecosystem is amazing. If I want to write a web server for my scientific application, 5 minutes and I have a web server. If I want to write an image library, a plot library, matplotlib, are all available at my disposal. I can immediately train differentiable models with PyTorch in the same code base. SymPy helps me to analyze symbolic expressions. Just that is an ecosystem that Fortran does not offer us, unfortunately. So what I want to say in this talk is that many important codes are written in Fortran. Fortran is a nice language, but we should really seriously be considering a Python-style language, going also towards NumPy for the better ecosystem. Or somehow pair these two up, have a Fortran Python ecosystem together. So see this with a grain of salt. But now let's look at a real code, a code that is used in production, the microphysics scheme or the cloud microphysics scheme of one of the most successful weather prediction application, the integrated forecasting system at ECMWF. That scheme has been analyzed by many researchers because it is incredibly important for performance of this application. So it's there to kind of deal with the fact that the resolution that we're running climate simulations at is not sufficient to resolve clouds. So it somehow resolves subgrid features that are not represented in the original grid with various heuristics. The original code is about 2,500 lines of Fortran 95. But however, it has been rewritten by a great team of engineers at ECMWF in C, optimized C, as well as C++ and CUDA at about the same number of code, which is quite interesting. So if you look at the original Fortran code, you see something like this. It's a typical Fortran code. Unfortunately here, this is what we are looking at here, these about 35 lines of code are literally just variable setup and initialization, and they go on until line 500. So it's quite an interesting code. I mean, these Fortran codes, they're all have a lot of variable setup and initialization parts in it. But now if we take this code and run it on a sequential CPU, this AMD EPYC here, we get a certain execution time. Let's call this 1.x. If we take the translated C code by ECMWF, then we will see that the C code is actually significantly slower than the Fortran code. So great, the Fortran compiler wins. A significant benefit, that was nearly 40%. So that is great. If you're a Fortran compiler, you are happy because you just beat the hand-tuned C version on a real machine, a real example. Now, if we actually look at one particular loop in this Cloud SC example, we could pick this loop here over KLEF and KFDIA, and we would see, well, this loop is actually fully parallel. It's fully data parallel. I can process every single iteration of this loop independently of all the other iterations of this loop. This is great. So the work in this loop, the number of iterations is KLEF times KFDIA, which is pretty obvious. But the depth of this loop, so the critical path we would have to process the loop in a sequential form, is 1. So it's perfect. So I have maximum parallelism. So my average parallelism is essentially the whole loop nest. My Fortran compiler is happy again with this loop. But while this is a representative loop at the Cloud SC code, it is not the only loop. There are some problems or some loops that look like this. And if you actually look at this, it's quite an interesting loop. It looks very similar. It's a two-dimensional loop. Right? Then it goes from 0 to n step, from 1 to n step minus 1, from 1 to KFDIA, which we've just seen before. But now what it does, it accumulates this array ZQXN into the last element, the element n step of this array. But it's doing this in a plus equals manner. So now these loop iterations are not independent anymore because I have this accumulation variable ZQXN JLN step, where I have to actually do it one by one. So this code is not friendly for parallelization. It's not written with parallelization in mind. Now the question is, can I extract this parallelism automatically as a Fortran compiler? Well, I can, but it's extremely hard. So what I would see as a normal Fortran compiler, I would see the typical work in this loop, just the iteration space, so the multiplication of the two variables. But I would also see the depth of this loop because I have a write after a read after write and actually a write after write dependency in this JLN step, which is not great. So I have two dependencies that are hard to deal with, and my average parallelism as a compiler, if I don't do anything else, would be 1. And this is unfortunate because as a human, you immediately see a way to fix it, right? So you could just say, well, why don't I accumulate this into local variables? Like if I was to parallelize this code, what I would do is I would just have, for each thread or each process, have a local accumulator and accumulate this array fully parallel at each thread into the local accumulator, but my Fortran compiler would not do this. So if as a human I would rewrite this, I would of course do it with a reduction tree. This is what I actually teach in the second semester at ETH Zurich in my parallel programming lecture. So any human can do this. I mean, any reasonable programmer would totally do it. The Fortran compiler will unfortunately not be able to do it automatically. Most Fortran compilers. Actually, we have not seen a single one who would do this automatically. So now if we look at more complex loops. So Cloud SC consists of multiple loops. So let's look at a real loop nest that we extracted from the code. Of course, there are thousands of these loop nests, again, 2,500 lines. So each of those has about 5-10 lines in the loop. So there's really, it's not thousands, but it's nearly 1,000 loop nests. So here we're just looking at 3, and we can analyze these loops again. Each of these 3 loops, we can analyze vark. We can analyze the depth that the compiler would be seeing. So we see that the second loop is wonderfully parallel. The first loop is not fully parallel, and the last loop actually is again wonderfully parallel. So here we look at this and we see, well, we again have this problem with these accumulator arrays. We can go a little bit more into detail, but really what it boils down to is that the reuse of this temporary variable, now it's even sadder, it's not even the array, but it's this ZQ ADJ, probably adjoint, is now reused twice. And of course, this is in this variable here. It's a write after write and a read after write dependency, as you can see in the top. So it's actually a bit more complicated. So what you could do, and again, it's relatively simple as a human, you could just privatize this variable to each thread. If you write OpenMP code, you would just annotate this and say it's an OpenMP private, and the compiler would actually do it for you. But the compiler, the Fortran compiler, doesn't do this automatically today, unfortunately. So what is the proposal now to help this poor Fortran compiler who cannot really analyze and parallelize the Cloud SC code? Well, the proposal is actually that we take the rained upon Fortran compiler and pair it up with a Sunny programmer, so a real human. And we bring the compiler together with a performance engineer. And if you've listened to talks of myself before, that is exactly what we call it, SPCL at my lab, performance metaprogramming. So the idea here is that we have a domain scientist working at the very high level, at the DSL level essentially, or at the Fortran level. So here we should be adding Fortran to this slide. And then we compile this code that the domain scientist writes in a very high level, so Fortran, DSLs, or anything else, into an internal representation that is a parametric data flow graph. We call these stateful data flow graphs, but that's the detail. And then we have a performance engineer, so another human, work on this graph representation where all of these dependencies that I just showed you on the previous slide for all of these loops are explicit. So you see those in a graph, and we'll go through an example in a minute. So this is quite nice. And then, of course, we have a code gen infrastructure that just generates CPU, GPU, and FPGA code. So how does this now work with the productivity? Well, at the highest level, the domain scientist only writes tens of lines of code. So as you can see in many frameworks, for example, deep learning frameworks, that the GPT code is only tens of lines of code, maybe 100. But then the performance engineer will already need hundreds of lines of code because he needs to unroll these things. But these codes, they can be reusable. So they can be transformations on the graph that apply to multiple different instances of the graph. So I may be writing a transformation for machine learning, but I can use that transformation later for deep learning, for scientific simulations as well. So for example, loop, unroll, and jam transformations would be one of those. They're usually hidden in a compiler, and you as a programmer, even as a hero programmer, you don't have access to them. But in the DAYS framework, we open those up. And you as a performance engineer or a hero programmer, you can actually write your own application-specific transformation in this framework. And then at the end, we generate thousands, if not tens of thousands, lines of code automatically to run at different target devices. So this is really the framework we are talking about in this particular examples. So I promised you the view of the performance engineer. So here you can see it on the left side, a little bit low contrast, but you can see that the data flow graph is fully represented. So all the data dependencies, all these edges are there. You can zoom in, you see loops. These are these things that look like hamburgers. So the opening and closing of a loop, and you can see tasklets. So as a performance engineer, you can now play with that view in any way you want interactively and transform this graph. So if you do this with the Fortran code, and here what Alexandru Calotoiu did is he wrote a Fortran front end for DAYS, so compiles the really unchanged, is the original Cloud SC code, into the DAYS intermediate representation, which we are seeing on the left. Then we do the typical performance engineering. Most of this already existed. And then we get a code that at the beginning of 2023, so when this talk was prepared for the Salishan meeting, actually was slightly slower than the original Fortran compiler. So Fortran was still at a win. However, just 2 weeks ago, we submitted a paper where we show how to tune that code to be 15% faster than the Fortran compiler. So we've now officially beaten the Fortran compiler with the same language. So when I say the Fortran compiler, it's of course GCC or ACC, the optimized compiler on the system. So great. So what do we do in this performance metaprogramming? Well, we expose parallelism. Like as I described before, many of these things are very easy to see for humans. For example, we change data container lifetime, we version data containers. This is equivalent to a privatization. And then we improve performance by changing data layout and do other things. So here are some examples where you could see these temporary variables. They're again quite annoying because here's across the loop iterations is a write after write dependency, and then you have a read after write dependency here. So quite annoying, but what you can do is you can just privatize this variable into a loop here, into an array ZADJ, such that each loop iteration, JLJK, as you see here, has its own local copy to be forwarded to the next line. And actually, you probably want to inline this, but it really depends if you what you want to do. I mean, these compilers, they then have their own ways of dealing with the fine-grained mechanics of the low-level interface. So wonderful. We essentially just privatized these variables to each iteration of the loop, and then we can parallelize the overall loop again. Of course, you immediately come up with better tricks. If you know the thread layout, you would be thread privatizing these variables and not value privatizing them through the whole iteration space. And this is, of course, something we did, but this is easier to explain here. So, and then we can apply all the wonderful tooling for performance metaprogramming that we have in the DACE framework. Much of this developed by Philip Schad, a PhD student in my group, also together with Tal Ben-Nun. And we can take these ideas to extract GPU kernels. So basically we can take the original Fortran code unchanged, parallelize it in the way I just showed you manually with transformations, but these transformations are pre-written as libraries, so it's not much work. And then we can lift it into a GPU transformation. And we can actually even test those automatically. So here we can extract the test cases to isolate side effects, because many of those transformations, because now the metaprogramming, we're writing a program that transforms a program. This is why it's metaprogramming, but we do this for performance reasons. We of course have to maintain the correctness of the program. And as we are all humans, we will make mistakes. We will write incorrect transformations that will rewrite the code incorrectly. And in order to make this simpler, Philip has developed this fuzzing scheme with other members of my team to automatically test these transformations and check them using automatic test methods, so-called fuzzing methods, generating randomized inputs, to check if these are equivalent to the original code. So this technique was basically also a paper accepted at Supercomputing 23 earlier this year, and Phil gave a talk that you can watch on our YouTube channel at the SPCL lab if you're interested in the details of this. So quite nice technique. So we can really generate hundreds of tests per second fully automatically without any human intervention. So this is quite nice. And then back to Alex's work on the Fortran front end. So now let's look at performance portability. We put all of this together. I told you about the earlier success that we beat the Fortran compiler by about 15% in a later paper. Here again, we still have the original results from a couple of months ago, but you can see the field is moving relatively fast. And then if you just run this in parallel, we already beat the Fortran compiler. So with 32 threads, we are running 20 times faster than the base case, which is slightly faster than the Fortran plus OpenMP version that people have written manually, and the C plus OpenMP version is still slower, so it's nearly a factor of 2 slower, in fact. So that is quite sad. But now let's look at the GPU version. And the GPU version is now fully automatically run on the GPU. It's 100 times faster. And it is about as fast as the Fortran plus OpenACC version, again, much manual work, and it's slightly slower as the C plus CUDA version. However, the tuning I explained earlier also makes that faster, so we are about the same speed as the C plus CUDA version, and we continue tuning that code. So that's an interesting one. So with this, I want to summarize this little kind of provocative talk that I gave at the Salishan workshop, or at the Salishan meeting, and many people asked me for it. This is why I'm recording it now. But as a conclusion, so DSLs are coming. We should be investing into writing new codes in Python. However, we may want to also not rewrite all these existing Fortran codes, because there are options to port these codes forward. After all, many of those have been in production for many decades and they're just working. So why would we re-engineer those without a reason? Yet new codes I would still recommend working with a better ecosystem. So we can do this with this particular example. I've shown Cloud SC. We're working on much more impactful codes in some sense. Cloud SC is just a small part of a weather and climate simulation. We are now working on a full weather and climate simulation under Alex's leadership. We apply the whole performance metaprogramming idea and gain performance portability, and we have an automated testing framework and really show interesting results. So we have full automation of performance portability. We do not have full automation of performance portability. However, we have this library of optimizations. So we can write manual optimizations, but we can reuse those across multiple instances. So this is what we call performance metaprogramming. So we achieve hand-tuned performance, and actually we are working on a full automation. This is why my Freudian slip just appeared. The full automation is then an AI-based method that we would replace big parts of the performance engineer. So make the performance engineer's life easier, such that the performance engineer just gives us some templates, and then a reinforcement learning based method, or actually vector similarity search based method, or various methods that we're developing, will be looking for the best optimizations for this particular code. So with that, I would like to close my talk. Thank you. We have a link to the YouTube channel if you're interested. There are many more of these videos also from my students going into much more detail. Thank you.